All right, we will continue talking about the reactivity of different acyl groups in nucleophilic substitution reactions. And the first consideration now, we're really going to start describing the trend in reactivity. The first consideration we'll make is the structure of the starting material. So I'm going to scroll back to what we covered in the previous video. We're talking about the structure of our starting material, so this here. And that's what we'll focus on in this video. So our first consideration, structure of starting material, carbonyl compound. Now remember, if we have an amide, an ester, a carboxylic acid, an acid chloride, or an anhydride, we have different structures of our starting material. So that's what we'll consider here. And really what we're focusing on is the resonance stabilization of the different Y groups. So the difference between those molecules. And then how that influences the carbonyl carbon electrophilicity. Now, the more electrophilic the carbonyl carbon, the more reactive that molecule is for nucleophilic addition. So we'll consider how resonance can impact the carbonyl carbon's electrophilicity. So let's do our general resonance scheme. So if we think about our general starting material, we'll still use that Y. Now, for all of our Y groups, they have at least one pair of electrons. They all have at least one pair. And so we'll draw the pair of electrons on Y. We have two pairs of electrons on the carbonyl oxygen. So another important resonance structure for these acyl groups that we're talking about here, where all atoms are closed shell, is when the Y electrons donate electrons towards the carbonyl carbon, and then that pi bond between carbon and oxygen breaks. So that would result in another valid resonance structure where we now have a pi bond between carbon and the Y group. The Y group lost ownership of electrons, so that became positive, and the oxygen gained ownership of electrons, so the oxygen becomes negative. So these are two important resonance structures, the most stable resonance structures for these general acyl group molecules, because all atoms are still closed shell. So when we compare our specific groups, we'll think about how the Y group, when that changes for the amides, esters, etc., how well that donates electrons through resonance. So let's start with amides. So amide structure, we have the acyl group bonded to a nitrogen. So if we just show the resonance here, it'll look the same for all of these, but we are donating nitrogen electrons towards the carbonyl carbon and breaking the pi bond. So resonance in the starting material for amides would look like this. Now let's draw the same thing for esters. And really carboxylic acids would have a similar resonance structure since the Y group is an oxygen for both of these, for both esters and carboxylic acids. So esters / carboxylic acids, we have our acyl group, carbonyl carbons bonded to an oxygen, and then we'll say that oxygen's bonded to an R group. If that R, we'll say that's R prime. That R is a hydrogen, it's a carboxylic acid. If it's a carbon chain, it's an ester. But either way, this oxygen has 2 pairs of electrons. And so this oxygen can donate electrons towards the carbonyl carbon, and that pi bond breaks, just like the previous structures. And this results in a positive charge on one oxygen, negative charge on the other. So we already can now compare the reactivity of amides and esters / carboxylic acids. Now we said amides are less reactive than esters and carboxylic acids. And this resonance can help explain why that is the case. When we're looking at resonance in the amide, the nitrogen is donating electrons towards the carbonyl carbon. And remember, if we have more electron density around the carbonyl carbon, that's a less reactive carbonyl carbon. Having less electron density around the carbonyl carbon makes that carbon more reactive so that the nucleophile can then come in and donate its electrons to create a bond. So really we're comparing a nitrogen donating electrons or an oxygen donating electrons. Well, oxygen is more electronegative than nitrogen. Oxygen holds onto its electrons more so than nitrogen does. So that means that this resonance that we're showing for esters is less significant in the ester molecule than it is in the amide molecule, because nitrogen is more likely to share its electrons. It's not holding them as tightly. Nitrogen has fewer protons in its nucleus, so it's more willing to share those electrons than an oxygen is. So let's write that note here. Oxygen is more electronegative than nitrogen. So resonance is less significant for esters / carboxylic acids than for amides. And this goes back to nitrogen groups being better electron donating groups. The electrons are more available since nitrogen is less electronegative, so these are better electron donating groups, and having a stronger electron donating groups makes the carbonyl carbon less reactive. Okay, let's continue on, and we will move to anhydrides now and compare reactivity. So in an anhydride, drawing out the general structure, we have the acyl group bonded to an oxygen, which is bonded to another acyl group. And so the oxygen between the two acyl groups can donate electrons in either direction toward one of the carbonyls. So let's say it donates electrons this way towards this carbon and breaks that pi bond. So now we have negative oxygen, positive oxygen with one pair of electrons now, and then our carbonyl over here. Now this electron donating effect of this oxygen does help stabilize this carbonyl carbon. So we're stabilized over here, but let's remember that the carbonyl carbon has a partial positive charge. Carbonyl oxygens have a partial negative charge. Even without showing the resonance, right, that partial charge is always present. So here, if we look at the carbonyl on the right of this, the right side of this molecule, we have a partial positive, I wrote negative, that should be positive, partial positive carbonyl carbon adjacent to a formally positive oxygen here. So that means that although we're stabilizing one of the carbonyls in this compound, the other carbonyl is destabilized. There's even less electron density around that carbonyl carbon. So that makes that carbonyl carbon more electrophilic. So if we add a note here, we can say repulsion of the O positive, the positively charged oxygen, and the carbon that has a partial positive charge. So we have two like charges that are on adjacent atoms. This is destabilizing. So that means that this resonance structure, the second resonance structure, is less significant. Or just this resonance from that central oxygen in general is less significant for anhydrides than it is for esters. So although in both esters and anhydrides, the atom bonded to carbonyl carbon is an oxygen, in anhydrides we have that destabilization effect when we show this resonance, when that resonance occurs, and so that makes the resonance less significant for anhydrides than for esters. Okay, now let's look at our last group, the acid chlorides. Drawing resonance again, we have acyl group, carbonyl carbon bonded to a chlorine. So again, showing resonance here, the chlorine atom can donate electrons to that single bond towards carbon, and we break the pi bond. That puts a positive charge on chlorine and, of course, negative charge on oxygen. So in this case, for an acid chloride, the electron, or the atom that could donate electrons, and we're showing that in this resonance structure, is chlorine. But what we know about chlorine is that chlorine's very electronegative. So it's much less willing to give up its electrons than an oxygen or a nitrogen. So that means that this resonance structure with the positively charged chlorine is even less significant than for anhydrides and less significant than for esters and amides. So our note here, see, chlorine is very electronegative. So it opposes this resonance interaction. There's another property of chlorines that's also very important here. And that's that if you look at chlorine on the periodic table, it's in the third row. And so that means the electrons in the valence shell of chlorine, so the outermost electrons for chlorine, are in the 3p shell. For carbon, carbon is in the second row, so its valence electrons are in the 2p shell. Having valence electrons in the 2p and the 3p, so 2p for carbon, 3p for chlorine, means that the overlap in the sharing of electrons is less significant. There is a weak electronic overlap here. So let's write this down. So the chlorine valence shell is the 3p shell. Carbon valence shell, 2p. So remember, reactions are happening with valence electrons, so outermost electrons. For a chlorine, that's the 3p shell. For a carbon, that's the 2p shell. And so between the chlorine and the carbon, we have a weak electronic overlap. So all of this means that this resonance is less significant for acid chlorides than anhydrides. Okay, so we've considered the resonance effect of all four of these different types of acyl groups. And so we can use this to explain that trend in reactivity. So we stated the trend in reactivity in the first video for today, where amides are less reactive than esters / carboxylic acids. I will say these were approximately equal. And these are much less reactive than anhydrides, which are less reactive than acid chlorides. So this is increasing reactivity, which was stated in the first video, part 1. Now, considering resonance and tying this into resonance, amides have the most significant resonance stabilization of that starting carbonyl compound. So we can say, now going in this direction, we have increasing resonance, stabilization, of the starting carbonyl compound. So increasing resonance stabilization of carbonyl compound, amides have the most resonance stabilization because nitrogens are most electron donating, so that makes amides the least reactive, and then vice versa for acid chlorides.